Welcome back to Swift Academy. If you watched our first video, you know we don't just memorize dry definitions. Today, we are diving into the next 10 essential Swift and iOS interview questions that technical leads use to separate junior coders from actual senior engineers. We're going to cover everything from memory allocation and state mutations to protocol-oriented design and data serialization. Let's jump straight into question 1. In Swift, what does the init method do? At its core, initialization is the mandatory process of preparing an instance of a class, structure, or enumeration so it's actually ready for use in your application. Its absolute primary responsibility under the hood comes down to safety. The initializer guarantees that every single stored property on that type is assigned a valid initial value before any other part of your code can touch it. A key characteristic to remember for your interview is that initializers do not return a value like regular methods do. Their sole purpose is to interact with memory to ensure your object's internal structure is completely stable, safe, and ready. The basic syntax is simple. You use the init keyword followed by parentheses, and inside the curly braces, you perform your setup, allocate your resources, or assign those required initial property values. To stand out to a tech lead, you need to show how initialization changes depending on the type you are building. Let's look at a class first. In our Network Manager example, notice how we are forced to write an explicit init, URL, string, block. Classes are reference types and do not get an automatic initializer. If you don't manually assign a value to properties like URL and declare a fallback for is connected inside this block, your code simply won't compile. Now contrast that with a struct. Look at our user profile structure below it. We defined our properties, but we didn't write an init method at all. Why? Because Swift automatically generates a member-wise initializer under the hood for structures. This allows you to instantly pass parameters like username and post count during instantiation without writing any extra boilerplate code. Finally, let's look at enumerations. While enums are fundamentally choices between distinct cases, you can actually supercharge them with custom initializers. In our app theme example, we can pass a Boolean flag like is dark mode enabled directly into init, run a quick conditional check, and dynamically assign self to the correct internal state. Explaining initialization through this specific lens of classes, structs, and enums proves to an interviewer that you understand Swift's strict compile time safety guardrails. Let's move on to the next question. Moving on to question number 2. State the control transfer statements present in iOS Swift. Control transfer statements completely change the order of your code's execution by moving control from one piece of code to another. First up, we have continue. This statement tells a loop to instantly stop its current iteration and jump straight to the start of the next one, skipping everything else below it. Next is break. When Swift hits a break statement, it immediately terminates the execution of the loop or switch block entirely, passing control straight to the code right beneath it. Then we have return. We use the return keyword inside our functions or methods to instantly exit the scope and optionally hand back a data value that meets our requirements. Finally, let's talk about fall-through. This is a massive favorite for interviewers because Swift handles switch cases uniquely. Unlike languages like C or Java where execution automatically bleeds into the next case unless you stop it, Swift has an implicit break after every single case. If you explicitly want a matching case to run its code and still fall directly into the statements of the very next case, you must use the fall-through keyword. Let's look at this exact example to see how it works under the hood. We have an integer number set to 1. Inside our switch statement, Swift hits case 1, which appends the string 1 to our description. Because we explicitly added the fall-through keyword right below it, control flow is instantly forced down into case 2, even though our number does not match the value 2. As a result, case 2 executes as well, appending 2 to the string. When we check our console, our final output reads, the numbers are 1, 2. Bringing up this explicit control behavior shows a technical lead that you understand exactly how Swift optimizes evaluation flow. Let's move on to question number 3. What are some common features in Swift structures and Swift classes? Interviewers love this question because it lays the groundwork for understanding Swift's architectural paradigm. To start, both structs and classes share a lot of modern DNA. They can both define properties or attributes to store state, and they can both define methods or functions to provide explicit behavior. Additionally, both types rely on initializers. Using the init keyword, both structures and classes build initialization blocks to safely configure their initial memory state before any other part of your application tries to access them. Architecturally, they can both be extended using the extension keyword. This allows you to smoothly append clean, new functionality, methods, or subscripts to existing types down the road without ever having to touch or rewrite the original source code. Crucially, both structs and classes can conform to protocols. They can adopt standard architectural blueprints to guarantee performance requirements, which forms the absolute bedrock of protocol-oriented programming in modern iOS development. Finally, they both seamlessly collaborate with generics. This empowers you to build highly flexible, reusable, and type-safe data structures that adapt to any data model you pass into them. Highlighting these 5 key intersections proves to a technical lead that you know exactly where value types and reference types align before you decide to separate them. Let's dive into question number 4. What is the difference between classes and structures in Swift? This is an absolute staple in iOS interviews because it reveals how deeply you understand Swift's memory and architectural design. Let's break it down side by side using 5 key pillars. First, inheritance. Classes fully support object-oriented inheritance, allowing a subclass to seamlessly adopt and override properties and methods from a parent class. Structures, however, do not support inheritance at all. They cannot inherit from other structures or classes, making them highly focused, flat data models. Second, and most importantly, is reference versus value semantics. Classes are reference types. When you assign or pass a class instance, you are passing pointers to the exact same location in memory. If one part of your app changes it, everyone sharing that reference sees the change. Structures are the complete opposite. They are value types. When you copy or pass a struct, Swift duplicates the data, giving you a completely unique, isolated instance. This brings us to their lifecycles and deinitializers. Because classes manage shared reference counts on the heap, they can use a init block to clean up files, networks, or custom resources right before the instance is deallocated from memory. Structures don't have pointers or reference counts. They live on the stack and disappear instantly when they go out of scope, so they cannot have deinitializers. Fourth, consider mutability. In classes, variable properties can be modified freely even if the instance itself is stored in a let constant, because the reference pointer hasn't changed. For structures, value integrity is strictly enforced. If a structure is assigned to a constant, its entire state becomes completely immutable, preventing any properties from being altered regardless of how they were defined. Finally, we have the identity check. When working with classes, you can use the identity operators, triple equals or exclamation double equals, to see if 2 separate variables point to the exact same object instance in memory. Structures don't have an underlying identity pointer, so they are compared purely on a structural level based on their property data using the standard equality operator. Clearly separating these core structural rules is exactly how you prove your command over Swift application health. Let's move on to question 5. What JSON frameworks are supported in iOS? When an interviewer asks this, they want to see that you understand both modern native solutions and the historical landscape of data parsing. Today, the absolute gold standard in iOS is the native codable paradigm, combining decodable and encodable. Using built-in tools like JSON Decoder, Swift allows you to map incoming JSON payloads directly to your type-safe data structures with almost zero boilerplate code. If you are dealing with unstructured or highly dynamic data where you can't easily predefine a model structure, Apple provides JSON serialization inside the Foundation framework. This is a lower-level native utility that safely parses raw JSON data into standard Swift dictionaries and arrays. Finally, it's highly valuable to acknowledge open-source frameworks like SBJSON. Historically built in Objective-C, SBJSON was a pioneer that added immense control, flexibility, and stream parsing capabilities to early iOS apps before Apple introduced robust native parsers. Mentioning the transition from legacy frameworks like SBJSON to modern native codable shows a technical lead that you understand how iOS architecture has matured over the years. Let's look at question 6. What is the use of the mutating keyword in Swift? To understand this, we have to look at how Swift handles memory. By default, structures are value types, which means they are completely immutable. Because of the safety rule, any standard function you write inside a struct is strictly read-only. It is completely blocked from modifying its own properties. To bypass this restriction, Swift gives us the mutating keyword. By placing mutating right before your function name, you explicitly tell the compiler that this specific method has permission to alter the struct's internal state. Remembering that mutating grants write access to value types is a perfect, bite-sized answer to ace this interview question. Let's look at a clear example. If we have a simple structure called demostruct with a variable property named foo, and we try to change that string inside a standard function, our build will fail. The compiler steps in with a clear error saying, cannot assign to property, self is immutable. To resolve this instantly, look at the right side. We simply add the mutating keyword directly in front of the function. This gives the method proper write access to modify foo with 0 errors. Explaining mutability, this simply shows an interviewer you know exactly how Swift handles value constraints under the hood. Let's move on to question number 7. What do you understand about protocols in iOS Swift? To put it simply, a protocol acts as an architectural skeleton. It defines a standard list of properties and methods required for a specific task. If you come from a background like Java, you can think of it exactly like an interface or a formal contract that ensures different parts of your code speak the same language. The crucial detail to emphasize to an interviewer is that protocols are a blueprint only. They do not contain any actual code implementation. They purely describe what needs to be built or expected, without dictating how to build it. This leads to universal adoption. Concrete types in Swift, whether they are structures, classes, or enumerations, can all adopt the protocol. Once they conform to it, they write the actual code logic inside to fulfill those rules, enabling highly flexible and decoupled application architectures. Now let's look at how we write this in code. On the left side, we see the basic syntax for a single protocol. We declare a protocol using the protocol keyword, here named demo protocol, where we outline our requirements. When a class, struct, or enum wants to adopt it, we simply use a colon after the type name followed by the protocol name. It's clean, direct, and easy to read. But what happens when your data layer requires behavior from multiple blueprints? Look at the right column for multiple protocols. Swift makes this incredibly simple. You just use a comma. If your class inherits from a parent superclass, you always list the superclass first, place a comma, and then list as many protocols as you need, separated by commas. This showcases the true power of protocol-oriented programming, allowing you to compose flexible behaviors without being restricted to single inheritance. Let's move on to our next question. What do you understand about plist in iOS, and what are some examples of its types? Plist stands for property list. It is a native file format using the .plist extension that developers use to store configurations, metadata, and application settings. At its core, a property list is structured as a straightforward key-value dictionary. It is intentionally designed to hold smaller amounts of data in a portable, lightweight manner directly inside the app bundle's file system, meaning you don't need to spin up a heavy database for simple settings. The most recognizable example every iOS developer interacts with is the Info.plist file. This vital file tells the operating system how to run the app, managing everything from your app's display name and bundle identifier to sensitive user privacy permission strings, like camera or location access keys. When it comes to how these files are formatted, iOS categorizes them into two main types. First, on the left we have the XML property list. This type stores data as plain text using standard XML tags. Because it is completely human-readable, it makes it incredibly simple for developers to open up, read, manually modify, and track cleanly inside source control systems like Git. Second, on the right we have the binary property list. Unlike plain text, this version is compressed into a binary format that isn't directly human-readable. However, it is highly optimized for performance, allowing the iOS system to read, parse, and load the configuration data significantly faster at runtime while keeping the app's installation footprint as small as possible. Let's move on to question 9. What do you understand about trailing closure syntax in iOS Swift? At its heart, Swift has a specific core rule. When the final parameter of a function is a closure block, the compiler allows you to change how it's written on screen to make your codebase cleaner. This is a classic example of syntactic sugar. Instead of passing the entire inline closure inside the function's standard parameter parentheses, Swift lets you pull it completely outside the closing parenthesis. It changes nothing about how the code compiles or executes under the hood. It purely changes how clean it looks. The immediate result of this is a massive boost to readability. It eliminates nesting clutter, drops bulky argument labels, and gets rid of those confusing trailing parentheses and brackets that typically pile up at the end of a block. It makes your code look incredibly elegant and effortless to scan. Let's look at this in practice. At the top, we define a basic function called runClosure after greeting. It takes two parameters, a string for the name, and a final execution parameter simply called closure. If we call this function normally, as seen on the left under traditional syntax, we have to explicitly pass the name string, include the closure argument label, open a brace inside the parameter parentheses, write our block, and then close both the brace and the parenthesis together. It works, but it's visually noisy and leaves trailing characters like, which can be annoying to track. Now look at how trailing closure syntax completely transforms this call. Because the closure is the very last argument, we completely drop the closure label and the trailing closing parenthesis. We close the parameter right after the string Sonia, and simply trail the executing block directly behind it. The code immediately reads like a native control flow statement, clean, readable, and highly professional. Let's dive into an essential architectural comparison. How do protocols and classes differ in iOS Swift? First, let's look at their core nature. A protocol is fundamentally an abstract definition. It strictly describes what an unknown sort of object can accomplish without creating an actual instance. A class, on the other hand, is a concrete blueprint used directly to generate tangible objects in memory. Next is implementation. Protocols enforce a strict code contract, meaning they contain zero internal code and never include function bodies inside their methods. Classes give you full code logic out of the box, allowing you to freely write complete method bodies and complex internal operations. Finally, we have storage. Protocols cannot provide any actual storage or physical backing stores for properties. Classes specialize in state storage, meaning they are fully allowed to hold and manage variables, constants, and data states in memory. Let's see how this looks in practice. On the left, we have the concrete class named car. Because it's a tangible object, it can be instantiated directly in your code, and it provides real, physical memory storage for its properties like this color string variable. Now look at the right side under protocol extension. While protocols don't allow immediate code implementation, Swift gives us an advanced feature. We can write extensions to provide default behavior. Here, we extend car to adopt custom string convertible, giving it a default computed property for its description. However, even inside these powerful extensions, the golden rule remains. You are still completely unable to provide stored properties or backing state. It keeps the separation of concerns completely clean. And that concludes our technical deep dive into these essential iOS architecture and Swift concepts. We've covered everything from the fundamental rules of mutating keywords and protocols to the syntax optimizations of trailing closures and structural differences of data storage. Thank you so much for your time and attention today. I'm looking forward to taking these concepts further and discussing how we can apply these exact senior-level architectural practices to build robust, scalable applications. Thank you.